This video is going to be an introduction to the Bernoulli distribution. I understand both Bernoulli and distribution are new words for us, so I'm going to start out this video by giving us two ways to think about the word distribution. Neither of them are formal, but they'll at least help us get started. Then we're immediately going to jump into R, really I mean RStudio, but I'm always going to reference it as R, and we're going to generate some fake data that follow the Bernoulli distribution. At that point, I'll give us some examples of what this data could represent to give you a better understanding of when and why the Bernoulli distribution might be interesting to statisticians. And then we'll close with properties of the Bernoulli distribution. So let's give this a go. So we're going to start with how to think about distributions. Okay, there's two general ways I want us to think about distributions. The first is a process that generates data. And now I don't care if that process is a computer and it's creating fake data, as we're about to do, or if it's a real world process. If you need something to attach your mind to right now, think of something even as simple as flipping a coin, but something more complex as an election with voters, where each voter is a process. Their outcome of the vote is some sort of process that generates data, their vote. So we're just going to say a process that generates data. And if the distribution is named, as it is the case here for a Bernoulli distribution, then the data will follow a pattern. Okay. So, for instance, the Bernoulli distribution has a very specific pattern that the data follow when the data come from this thing named a distribution for the Bernoulli. So the Bernoulli distribution generates a very specific pattern of data. Okay, the second way I want us to think about distributions is that there exists a mathematical representation for named distributions. Specifically, functions. There exist functions that represent these distributions. But for now, we're not going to get too carried away on the function side. I just want you to know that there exist mathematical representations for these named distributions, and those mathematical representations define the pattern that the process generates data by. Okay, so here we go. The first one is a process that generates data, typically in a pattern, and there exists a mathematical representation that describes that pattern. So here we are in R. We're going to first declare some variables. I'm going to use the capital letter N, and I'm going to kind of arbitrarily pick the number 7. And this is going to be, in general, I'm going to use the capital letter N for the key word, that is, add this word to your course notes, the sample size, the number of data points. So the sample size is the number of data points. For now, I just kind of arbitrarily picked 7 to say we will generate 7 data points. And I'm only picking a relatively small number here because we're going to look at the data we generate in order to help us learn things about the Bernoulli distribution, and I don't want us to get overwhelmed with the amount of data we generate. It's pretty easy to get overwhelmed with the amount of data you generate in R. The next variable we're going to create is going to be P. I'm going to pick 0.5. This is going to be a probability. That's why I've named it P. And for now, I want you to think of a fair coin. So in order to generate data for a Bernoulli distribution, we're going to use a function that starts with the letter R, which stands for randomly generate. And then it's named binom. So R binom is the name of the function, and we will explain later in the class what binom means. This is a function, so after the name of the function, there's parentheses into which go arguments. The first argument is going to be the capital letter N, how many data points we want. The next letter for Bernoulli data will always be a 1, and then P. So now this function, R binom, depends on two variables, P and N, which I have not created yet because I have not run these lines of code yet. Okay, so let's give that a go. I'm on a Mac, so I'm going to hold Command and then hit Enter. If you're on a Windows machine, hold Control and then hit Enter. Holding Command and hitting Enter once and twice, you can see the code for both N and P to be assigned these values was sent to the console, and you can see that they showed up over here in our global environment. Next, I'm going to hold Command because I'm on a Mac. If you're on a Windows machine, hold Control and hit Enter. And lo and behold, we generated 7 data points, the first of which was a 0, the second of which was a 1, and then the third, a 0, fourth, a 1, fifth, sixth, and seventh data points, 0. So this is a sequence of Bernoulli data. Specifically, the sequence is length 7, and this probability describes the probability that we observe A1. So let's just note that. Now, you all will learn to love, eventually, I hope, the delightfulness of randomness. That is, here are 7 data points. Maybe you expected more 1s than just 2 to show up. But just by chance, that's all we got. If we run this code again, we're going to get maybe more 1s. Maybe that's more than you expected this time. Oh, that's fun. Isn't randomness fun? Let's just try a few more times. So every time you run this code, you see what's happening is we're getting new data because it is randomly generating the data. The only consistent thing about this is that because it's a Bernoulli distribution, there's only 0s and 1s. And because we chose P, the probability of observing a 1, to be 0.5, each time it draws a new data point, there is a 50% chance of getting a 1. And hence a 50% chance of getting a 0. Now, the way I want you to think about this Bernoulli distribution is, let's get rid of, okay, you know what I want to do? I want to store our data into a variable named x. So I'm just going to rerun this one more time. Now you can see x is created. Watch this, is.vector x. Aha, all this vector business is coming back here. We now have a vector of data named x that consists of randomly chosen 1s and 0s, where the probability of a 1 showing up is 0.5. The way I want you to think about the Bernoulli distribution is like this. Imagine for a second, all you had was data. 1, 0, look how many 1s that is, isn't that fun? All you had was 1s and 0s. This is a good representation of Bernoulli data. Bernoulli data is only ever 1s and 0s. In this case, what we've essentially done is simulated a fair coin. In this case, what you've done is flipped a fair coin 7 times using a computer. But theoretically, this data could represent any process for which there are only 2 outcomes, 0 and 1. For instance, if you're interested in the probability that you are going to pass this class, Well, you'd certainly want that probability to be very high, but you probably don't know what that probability is. One way to find out via the world of statistics is to go collect yourself some Bernoulli data. You take a randomly sampled student in one of my previous classes, and you ask, did they pass the course? And the first student said yes, so you mark them a 1. Then you ask another randomly chosen student, and you ask them if they passed, and unfortunately the second student did not pass. But lucky for you, you can ask 5 more students, and all of them passed indeed. The great thing about Bernoulli data is all you need is a vector of 1s and 0s, and you can estimate that underlying probability. Now, if all you have is 7 data points, you're not going to get a very good guess, but you could, theoretically, sample more students. And if all you had, notice on this last line is, all you had was the data, then that's all you need. You could estimate the probability of passing the class. Oh, not very good odds. Only like 50%. Okay, that's not the takeaway here. The takeaway is, look, with more data, now 700 samples, we have a very good guess of what we know to be the true probability. This is going to be a game we play in this class. Because we have the access to computers, we're going to simulate fake data to see that we can estimate things like probabilities of observing a 1, whatever that 1 represents. Let me give you another reasonable example. Chrome, the web browser, as developed by Google, is highly tested. The browser is highly tested such that if you randomly choose a web page on the internet, the developers of Chrome want the web browser to display that web page correctly. So they want there to be a very high probability that Chrome displays any chosen web page correctly. What they really want is something like probability of displaying a web page correctly, call it a 1, to be something close to 0.95. And the probability of displaying a web page incorrectly, 0, to be quite small. In this case, we know it to be 0.05. So let's just redeclare these variables, generate some data, and now make believe. Now, if we were Google developers testing the web browser Chrome, all we might have access to is 700 data points, where each one of these is essentially a new randomly chosen web page where they tested, does Chrome display that web page correctly? If the web page is displayed correctly on Chrome, mark it a 1. If any given web page is not displayed correctly, mark it a 0. And with only that data, look what you can do. You can estimate quite accurately the probability that Chrome displays the web page correctly. This is the Bernoulli distribution. We are often going to generate fake data to help you understand some key facts about about new distributions, specifically here, the Bernoulli distribution. So, with that in mind, we should ask the question, what are some properties of the Bernoulli distribution? First one, only 2 outcomes. Any process that generates data where there's only 2 outcomes, 0 and 1, is a really good candidate for a Bernoulli distribution generating that data. Mark as 1 the outcome of interest. Whatever your outcome of interest might be, just call it a 1 and call the outcome you're less interested in a 0. There is some probability of 1 call it P. We believe P is in the interval of real numbers consisting from inclusive 0 to inclusive 1. As you saw when we generated fake data, we claimed to know the value of P. But as I was trying to allude to in the example about Chrome, the web browser, you don't have to know the value of P. So long as you have a vector of data, you can estimate the probability that your web browser Chrome displays a randomly chosen page correctly. There exists some probability of observing a 1. We call it P, and we believe that probability lives in this interval of real numbers. Okay, third property. No two outcomes are related. Let me give you an example of this. This is like saying if Google developers went and randomly sampled 3 web pages. Say the first one loaded correctly. Because the first web page loaded correctly, does that tell us anything about the second web page loading correctly? It does not. Even though the first web page loaded correctly, we don't know anything about the second web page loading correctly or not. So the first and second are not related in any way. Because the first randomly sampled web page loaded correctly, does that tell us anything about the third randomly sampled web page loading correctly or not? It does not. So the first web page randomly sampled doesn't have anything to do with the second, and the first doesn't have anything to do with the third. Now, does the second web page loading correctly or not have anything to do with the third web page loading correctly or not? No. So long as you take a random sample, then they're probably not pages from the same site. So these are the key properties of the Bernoulli distribution. So long as there's only 2 outcomes, there exists some probability of observing a 1, and no 2 outcomes are related. As long as these properties fit your process of interest, then statisticians will tend to believe that a Bernoulli distribution generated the data.